statistics, and specifically more also on the kernel density estimation part, because that is a very important topic. However, much exposure is not there on that topic in the master's level. So I would like to shed light on this kernel density estimation part. So actually, specifically kernel density estimation, I chose, because what to say, because of the versatility of the non-parametric statistics and the practical significance in data analysis it has. The non-parametric methods actually stand out because they actually do not rely on the strict assumptions about underlying data distribution. So that is a very important point of this talk, because we do not have to make any prerequisite assumption, so we can directly go ahead with whatever we have. So that makes the analysis more powerful, that even if we do not have any assumptions, we can go ahead with that. So that makes them very highly adaptable and robust for all these real world applications. And specifically I chose KD as a centerpiece of this discussion, because I feel that it is a very powerful and intuitive tool for estimating the probability density functions of a data set. Because see, unlike histograms, what the problem is, unlike histograms which can be actually rigid and dependent on bin size, the size of the bins that are actually there in histograms, KD provides a very smooth and continuous estimate of the data distribution. So, which makes them very useful in uncovering patterns, identifying modes, or maybe even detecting anomalies without some prior assumptions about the data shape. So, actually, its flexibility and wide applicability makes it a cornerstone of modern non-parametric analysis, perfectly aligning with the goal of exploring data without assumption, which is actually the key theme of the talk. So, actually, I'll share my screen now for the presentation. Just tell me whether it is visible to you or not. Mm, just a second. Okay, is my screen visible, Moitro? Okay, okay. Okay, so I will now start my presentation. Okay. So as you can see, this is the title of the talk: Precision Without Assumptions: The Science and Application of Kernel Density Estimation, a very cornerstone topic of non-parametric analysis, which I will be talking about in the UGPG lecture series. My name is Arkajit Banerjee. I am a first year MSc Statistics student at the Department of Statistics, University of Kalyani. This is my email ID. Both my personal and my institutional email IDs, both are there. So anybody feeling to contact may please do so. Okay. So the flow of the talk will be, we'll be discussing why non-parametric statistics. Firstly, we'll be discussing about non-parametric statistics. Why do we need non-parametric statistics? Practical uses of non-parametric statistics. Kernel density estimators. What are discrete estimators? What are kernel functions? Estimation bias and estimation variance of these, kernel functions. And then we'll be discussing two very important topics about the asymptotically optimal bandwidth and asymptotically optimal kernel, which actually be helpful for estimation of these kernel functions. And finally we'll be seeing some rule of thumb, if it is there or not, for bandwidth calculation, for the optimal bandwidth calculation. Okay. uh, so yes, so let's start with a real world scenario or a real world problem statement. Imagine that you are a data scientist working in a healthcare setting where you are studying about a group of patients with a rare and complex disease. Okay. And the patients vary widely in their age, lifestyle, the severity of symptoms in response to treatment. Okay. Now, their symptoms are varying widely, and you do not know that if they follow any specific pattern or any distribution or not. So, what are you trying to do? You are trying to study a group of patients who are having a very rare and complex disease. However, the symptoms are very widely varying, and you do not know if they have a very specific pattern or not, or any particular distribution they are following or not. And since you are making an analysis on a rare disease, so the data set available to you is also small. It is since it is a rare and complex disease, much research has also not has been done because it is not a very common problem. So typically less literature is available for you on this particular topic. So, and you typically would like to understand the data, make predictions, or test hypotheses. How do you do that? In traditional statistics, which are actually called the parametric statistics, you would be generally assuming a specific shape or the distribution of the data, like say normal or bell curve. But this assumption would actually make your analysis simpler and give you a precise formula to work with. For instance, suppose say if you have assumed the patient ages are following normal distribution, then you could very well use some mean parameter or some variance parameter to use them and analyze the age related factors. But here, those assumptions might be misleading or entirely incorrect because the disease doesn't follow only any similar patterns or standardized characteristics. So everything is very much random, and you do not. And the most important thing is that you do not have any particular information on the randomness. And the more important fact is, if you try to force a normal distribution on this type of data, you might miss out very important insights. So the symptoms are very so suppose say might happen that the symptoms are common among suppose say young and older patients, creating bimodal distribution. So bimodal distribution might come up, or maybe the distribution is skewed. It is non-normal. So forcing this data into a normal distribution wouldn't capture these what do we say these nuances. So it might oversimplify the process and and might obscure the critical information, which may even lead to incorrect conclusions. So the challenges which you might be feeling here is actually the size of the data set is small. As I told you, it is a rare and complex disease, so you might be not be getting enough data on this. Not considerable amount of literature will be there to you. Challenge to make any distribution assumption due to less resource availability. That is what I said, because distribution assumptions can't be made because you do not know very much about it. Okay, you do not know about the specific pattern is there or not, much information about the population, how it is, and always the normal distribution will not come to your rescue, as we have already been taught in college that in the bachelor's level that you try to model things by normal distribution, but that is not how the real world works. Everything in this world is either skewed or maybe bimodal, or very few data is there which actually directly fits into normal distribution. So non normal distribution, forcing everything on normal distribution won't yield a very good result. So non-parametric statistics enters the market here. And unlike the parametric methods, these non-parametric methods do not require any assumptions to be made about the shape or distribution of the data. Instead, what they allow is they allow us to analyze the data as it is with all the irregularities and unique characteristics. And this flexibility means you can explore and analyze the data with an open mindset, allowing the patterns and all the trends to emerge naturally. How it will be done, I'll be discussing in the due course of the talk. With non-parametric statistics, actually I want to discuss three important points. It identifies the real patterns. What it does is, see, suppose if there are any clusters or symptoms, or might be the fact that suppose say if suppose say that if there is not a typical distribution fit, then non-parametric approaches can reveal those clusters without forcing them to go for a standard model. Even if there is not a very good fit, then also non-parametric statistics can reveal similarities and all these trends, or anything of this kind, or clusters or symptoms which the patients are having, say. So patients data set is just a very sample problem, just a sample problem. But these non-parametric statistics approaches can actually reveal those clusters without forcing them to go for a standard distribution fit. The natural shape can be analyzed by methods such as kernel density estimation, which will be the main highlight of the talk. And finally, the misleading results can be avoided because without strict assumptions, we can reduce the risk of distorting the data into a predetermined model. So, which can lead to false insights, especially in medical contexts when the accuracy needs to be paramount. Okay, next we'll be going for the next topic, that is just a sec. Yes. So the broad aspect of inferential statistics is actually it is a branch of statistics that helps us to make some decisions or predictions about a population based on a sample. Since it is often impractical to study an entire population like surveying every single person in a country, what we collect data from a subset, like from a sample, and then use this information to draw inferences about the whole population. Okay, population, we all know that it refers to the entire study group that we want to study or draw conclusions about. The sample is a smaller group selected from the population, and we study the sample, and then based on the characteristics, we estimate the characteristics of the population. There are various methods of drawing sample, which is actually a dedicated paper in MSc statistics, or the sample survey methods. A lot of methods are there about how to draw sample, which gives good, good samples. Like better data can be analyzed in like, and then comes the major two portions of inferential statistics. One is the estimation theory and one is the hypothesis testing. I'll just briefly tell what is estimation theory. So estimation theory actually involves using the data from the sample to estimate a population parameter. So there are two main types of estimates which we deal with in our daily work. So one is something called point estimate, which is a single value estimate, like using a sample mean to estimate a population mean or maybe the variance counterpart. And we also do the interval estimation, which actually provides a range or a confidence interval that is likely to contain a population parameter, adding a measure of uncertainty to the estimate. Okay, so there is an interval that the value might be lying from this range, like within a range from this value to this value. So you are specifying interval without giving a particular point estimate. So we'll be saying here that the value lies between this range. So this is actually estimation theory. And hypothesis testing is what it does is it allows us to make inference about the population by testing assumptions. Because if you tell that my this, suppose say any value has come up to this, so with how much degree of confidence you are saying, that needs to be understood, because we randomly cannot accept your discussion that or any value or any claim that you are making that okay, this is 100% true. So we need to examine that with what level of accuracy, with what level of confidence you are telling that this might be true, and if it is not true, then what is the other alternate claim that is happening. So the claim that you are making, the claim that is being made by the researcher, that there is no effect or no difference, that is called a null hypothesis. And the alternate hypothesis is there is some difference or deviation from the null hypothesis. And based on the sample data and using some parametric hypothesis tests, we either reject the null hypothesis or we fail to reject it. Here, a good point is we never say that we reject the null hypothesis or accept the alternate hypothesis. No, we don't say it like this. We always say everything with respect to null hypothesis. So either we reject it or we fail to reject it. The acceptance is not a very good word with the statistical community. Okay. Acha, now, these three concepts which I have written about parametric statistics, non-parametric statistics, and Bayesian statistics, just a very brief thing about what they are. So, in parametric statistics, as I've already discussed prior also, that we assume that the sample comes from a population with specific distribution, often a normal distribution. So, which makes actually our estimation procedure more simpler, as long as the assumptions hold. Very important point, as long as the assumptions hold. And here the estimation approaches actually are parametric methods are using formulas for confidence interval based on assumptions about the population, mainly the t distribution for small samples. And the testing of hypotheses are usually the ANOVA tests or the the t-tests. So these are the parametric tests, and they assume that the sample data follows a normal distribution. So if the assumptions are valid, these tests are very much efficient. But if they are not, if there are no assumptions which are like we cannot make any assumptions, or the assumptions are not valid, invalid, then we come down to the next part, which is the non-parametric statistics. Non-parametric statistics doesn't assume any specific distribution for a population, making them very much flexible to applicable to any type of data, which do not meet even the parametric assumptions. And in estimation, the non-parametric estimation, which today I'll be talking about, is the kernel density estimation. Actually, it is an estimation technique only, very much useful in providing smooth estimates of the PDFs of data without assuming any particular assumption or having any information about the prior population form. So KDE actually is helpful when we want to understand the distribution of population without relying on normality. That is what I was telling. And finally, Bayesian statistics is actually this Bayesian statistics incorporates prior information or beliefs into the inferential procedure. And what we do is we update this information continuously based on the new data or the new sample. And Bayesian estimation, one point about Bayesian estimation, what I would like to make is that they do not give a very single point estimate. Instead, what it provides is it provides a posterior distribution. What happens is that reflects actually our updated beliefs. So it is not that it is giving a point estimate directly. It is giving a posterior distribution, which actually reveals that the updated information about a population parameter, with respect to a given sample. And there are some methods which actually are used in Bayesian methods, which are mainly one very important part is called MCMC, which is Monte Carlo Markov chain Monte Carlo, which allows us for complex estimation testing that can account for uncertainty and prior knowledge. So this was about a very brief, talk about inferential statistics. Inferential statistics. Then we move to a small comparison on parametric versus non-parametric. As I said, that model specification is solid distribution assumptions are made by parametric, whereas in non-parametric, no strict distribution forms are there. Complexity is in parametric, this finite dimension, so limited number of parameters we are working with. But in non-parametric statistics, since we do not have any information about the data, so it might be the case that we might even need to work with infinite number of parameters. It is purely data driven, purely. Conversion rates, when we are talking about it, it is actually 1 by root n parametric, and non-parametric actually it is converging at some rates slower than 1 by root n. And the fitting part is that, okay, here in parametric the fitting, like how do we say it, what is the approach in parametric? We say that how close is the fitted model to the true one. It will be it will be close to the true one, that is for guarantee. How much close, that is the test of parametric. Like, you know what do we say, that the validation, that how much good my model is performing, we usually say that as validation, that how much good my model is performing. Here the validation, how we talk about this thing is that how close is it with the fitted model. It will be close, that is guarantee. How close, how much is the intensity of closeness, that is for parametric statistics. But in non-parametric statistics, you cannot tell anything because it acknowledges the fact that there will be some differences. There will be, a deviation from the true model and the existing model which I am proposing, which the actual the population is, and the estimate which I am trying to give. So it acknowledges the fact that there will be some differences. So it should be seen as a sort of approximation approach. Okay. Ajay, before going for the directly jumping into theory, we should be motivated enough to see some use cases of non-parametric statistics and where it can be useful. See, in the healthcare and medical aspect, actually in the survival analysis, this non-parametric statistics is used. In clinical trials, non-parametric methods such as Kaplan-Meier estimator are actually used to estimate patient survival times. And how these treatments are compared, I'll tell you. There is a test called Mann-Whitney U test or Wilcoxon ransom test. If there is time, I will surely discuss about it later. So this Man-Whitney U test or this Wilcoxon ransom test, so that is actually done to compare the different outcomes. So maybe examples, a pain scores, recovery time between the two treatment groups. So these tests are very useful because patient responses are often skewed or have outliers. So in this case, the non-parametric methods are much more reliable. Get my point? And what are some diagnostic tests which are actually occurring here? So non-parametric methods are using to evaluate the performance of diagnostic tests. For example, say the ROC curve, which is actually the receiver operating characteristic curve. So they do not assume that a specific distribution of data is there. helping in assessing the sensitivity and specificity of the diagnostic tools without any assumption of normality. So you can understand the robustness of non-biometric statistics in healthcare and medicine unit. Second, when we come to the finance and this risk assessment and this portfolio analysis, what is there is actually financial data like returns on stocks. So this is actually one of my major areas of research. I like to work on mathematical finance. So financial data like returns or stocks or other assets often have skewed or heavy tailed distributions. Okay. So non-parametric approach such as KD, what it does is it helps in estimating the probability distributions of returns and understand risk without actually assuming that they are assuming a normal distribution, because most of the time when you plot finance data you will be seeing that they are heavily skewed. Heavily normal data is not there in doesn't exist, I think, in finance. The amount of data I work with, I have not seen any uh, normal data, or data which is having some bell-shaped structure. So here, run tests are very useful for this test of randomness in the stock price movement. So run test is again a non-parametric test, and when there is, suppose, say, income inequality or say economic data. So economic data such as income distributions are again, so income distributions are also positively skewed. So non-parametric tests like the Kolmogorov-Smirnov test, the case test, so which can actually compare the income distributions across different regions or demographics without making any distribution assumptions. So that is again a very powerful aspect of non-parametric statistics. Next, again we have some practical use case such as quality monitoring and manufacturing. So non-parametric control charts, which are actually called the CUSUM chart, CUSUM chart, or the run charts. So these are useful for the quality control and monitoring for the SQC, which is actually basically, and these charts monitor the process without assumption of the fact that the distribution might be normal. And again here the Man-Whitney U-test can be used. And in reliability testing also, non-parametric tests are used in reliability and failure time analysis. So again, as I said, that the Kaplan-Meier estimator is very much useful for all these things. And the today's world runs on machine learning, data science, AI. These are the buzzwords of today's market, today's industry. So here what actually non-parametric statistics does is, the KD is very widely used in anomaly and outlier detection, which actually detects or identifies unusual data points without assuming a specific distribution. So here again, some non-parametric randomness tests are there, such as Wilcoxon rank sum test, suppose, which are often used to assess the feature importance in machine learning, especially with non-normal distributed data. Again, there is something called the density estimation for clustering. So KD, which will be the main thing for my talk. So KD can identify high density regions. So high density regions means clusters in complex data set without assuming a specific shape, making it very much vulnerable in image segmentation and customer segmentation and biological data segmentation analysis, further analysis. So these are just four typical practical uses of non-parametric statistics, as I said. But as you dig into it more, you will be finding huge amount of work that can be done using non-parametric statistics. A brief introduction on non-parametric statistics. So I'll just explain what are the non-parametric statistical objects which are of prime importance to us. So that actually include something called the density function, univariate and multivariate, both aspect, density derivative, conditional density function, conditional distribution function, regression function, median function, quantile function, and variance functions. And as I said, the non-parametric methods typically involve some sort of approximation or smoothing method. Okay, so it is so, and the main methods which are used are for the non-parametric statistics are the kernels, series, and splines. As I'll discuss everything here, that what each of these individual term means. And one thing is that very important thing, that these non-parametric methods are typically indexed by something called the bandwidth or the tuning parameter, which controls the degree of complexity of the the estimate or the graph which will be generated by us. To give you a very brief explanation of non-parametric objects of interest, actually Suppose say what we call this regression function, quantile, density function, variation function, all these things. These non-parametric estimates are actually used directly for analysis. Okay. However, some other times are they sometimes serve as inputs in estimating simple and parametric quantities. Then it becomes a two-step approach, and then it becomes a semi-parametric approach. Okay. So I'll just very briefly discuss what each term means, what the density function and the regression function. Very briefly, I'll be discussing about this thing. The density function actually describes or determines how the data points are distributed over a range of values. So for continuous data, it represents the likelihood of finding the data points in the different regions. And for the non-parametric estimation, that is a kernel density estimation, is actually a very common approach, common parametric non-parametric approach for estimating these density functions. So that is what we will be learning today. That how these things actually work. What is the theory of this KD? So KDE places a bump which is actually shaped by the kernel function at each data point and then smooths it to estimate the overall shape of the data's distribution. What the advantage is that it allows us to see whether the data points are most concentrated without assuming a specific distribution like normality. Secondly, when you come to something called as regression functions, so regression function is something which represents the relationship between an input, an independent variable, or an output, which is a dependent variable, and it shows how the expected value of output variable changes with respect to input. And methods like local regression, which is actually called LOESS. So that is the the short form LOESS. It is not so lowest actually local regression and smoothing the spline fit flexible curves to the data by using the nearby points allow us to make the local predictions. Speaking about the quantile definition, quantiles are actually points in the data distribution that divide it into specific intervals with specific probabilities. So, for example, if we say that the median 50th percentile is the middle value, while the sorry, while the 25th and the 75th percentiles are actually called the Q1, Q3, first quartile and the third quartile respectively. So non-parametric estimation here actually involves arranging the data points in ascending or descending order and determining the value at each quantile position. Okay. So this approach doesn't require any assumption about the shape of the distribution, making it very robust and adaptable to specifically, the skewed or the irregular distributions. Again, say we do have the variance functions. What are variance functions? Variance functions can be described as how the variability. Just a second. Yes. Yes, so the variance estimation and the variance function can be defined as how the variability of the data set might be changing with respect to another variable. That is the matter of question. It can be used to measure the speed or dispersion of the data point around the mean. And the role of non-parametric estimation in the variance functions is that some local variance estimation function methods are actually there, which allows us to estimate how the variance changes across the different regions of the data without assuming a constant variance. And so basically this approach is a heteroscedastic approach, so we are not making any assumption that this is going for a for constant variance approach. It's a heteroscedastic approach where it is particularly useful in some situations where the variance might depend on factors such as maybe say time or maybe say another variable. So a heteroscedastic approach is coming into factor. So smoothing techniques like KD can be very much useful in estimating this local variance. Local variance, well, I am telling that because this is being done with respect to different regions. So regional analysis is being made. So it doesn't require any distribution assumption, which actually helps us in doing all this analysis when data is when we do not have much prior information about the data. So and when we do not have prior information, so Bayesian statistics also can't be applied. So the only method which is there is non-parametric approach, and non-parametric approach is very much powerful. And these terms, what I said, that what is a kernel? Actually, kernel is which is used in the kernel density estimation technique is actually that each data point is contributing to a small bump in the density. That is actually in the long term that is smoothed out. In the series approach, what happens is we expand the data using some functions like sines or cosines. Okay, and the spline approach is that uses some piecewise functions that are smooth at certain points. And the role of bandwidth, as I said, that this is typically indexed by something called a bandwidth or the tuning parameter. So bandwidth is actually what it does is it sorts of controls the smoothness or the complexity of the non-parametric estimate. So suppose say if the bandwidth is too small, then the model will become jagged and overfit. Okay, and if it is too large, then the model will become over smooth. It will overfit, and then will miss the important details. So choosing the right bandwidth is crucial. So we'll be seeing some rule of thumb which is there actually, and the generalization from a univariate density estimation is that many non-parametric approaches are built around the univariate density estimation technique. And by understanding this theory behind the univariate density estimation, we can extend these principles to complex scenarios such as multivariate density estimation, making it making it more robust for non-parametric multivariate analysis. We'll be starting with univariate, and then might be we can make it even more stronger for the non for the multivariate part. Okay. So now actually we'll be starting with something called a kernel density estimator, which is actually the discrete estimator. Now I will tell you the theory behind this discrete estimator, that why we are using a discrete estimator. So in this non-parametric statistics, we often want to estimate something called the fx. This is the density function, right? We want to estimate this density function of a random variable x, and this is without assuming that we are having any specific mathematical form for the distribution. So we'll be discrete estimator approach. So the problem statement will be such that we have a random variable x which is having a cumulative density function fx, capital Fx, okay, and then we will be having a density function of a PDF which is called the f small x, where we can obviously we can write this as fx equals to t dx of capital Fx, right? So our goal is to estimate this small effects on the PDF using the sample x1, x2, x3, xn of the observed x values. Now here I'll introduce you to one term which is called the EDF. Okay, EDF, empirical density function. I'll just tell you what it is. The empirical density function is actually a step function which provides a non-parametric estimate of the cumulative density function of a random variable directly based on observed data. The EDF can be written as actually EDF's formula. I'll just write it down for you. F cap, which will be said as 1 by n summation 1. This is the standard formula for EDF. What actually it does is, or okay, first understand the meaning of this particular part. What does this particular part mean? This is actually an indicator function that equals that one, that this function will be equal to 1 if this condition is there, that x1 is less than x, or 0 if otherwise any condition is there. So this actually means that fx is simply the proportion of sample points that are less than or equal to x. And how EDF differs from CDF, that is a very important concept, that the nature of the function is actually a step function where the size is of step 1 by n, and approximation of the CDF. So EDF is approximating the CDF. Okay. And as the sample size increases, this EDF is actually converging to the CDF by the Glivenko-Kandel theorem. So there is a theorem called the Glivenko-Kandel theorem which actually states that the EDF converges to the CDF when the sample size actually increases. And the interpretation is, while the CDF gives the probability that the suppose say that the random variable x is less than or equal to x in the entire population, EDF gives that the observed proportion of sample points that are less than or equal to x. EDF is simply just sort of an empirical measure which is solely based on the sample at hand and not the entire population. So it is just dealing with the sample which is actually being given there. And uses of the EDF, there are primarily many uses of EDF. Why I'm telling EDF, because I'll be needing this when I will be discussing about what is called the discrete density estimator. The use of the EDF is just about the goodness of fit test. So there are various goodness of fit tests, as the Kolmogorov-Smirnov test and hypothesis testing like the Man-Whitney U test, or the Wilcoxon ranked sum test. So all, or the Wilcoxon signed rank test also. So all these things are actually based on the EDF, goodness of fit. Uh, okay. So these tests actually compare the EDF of a sample with a specified theoretical CDF to determine that if the data came from a specific distribution or not. Now, here you might be able to see that I have written the formula as fx equals to this ddx of fx. But you know fx is a derivative of this, but it might seem logical. It might seem very logical to write that we can directly take derivative of this particular EDF function, and we directly get fx, which is actually our target function which we need to estimate. This is given. This is the EDF. And it might appear that since fx is actually can be written as ddx of capital F, which is the density, the distribution function. So why can't we take the derivative of this particular function? That is a very important question. Because you simply can't take the derivative because it won't be giving you a smooth density function. It would just be a set of mass points and where the jumps are happening. Because as I said, this is a step function. This is not the cumulative density function. Okay, so if you are directly taking the derivative of this particular function, so you won't be getting a very good estimate of the PDF, because it will not be a very smooth or a very a very what to say, sort of that smooth function. It will be sort of a mass points will be given, that where the jump has occurred, there a mass point will come out. So that is not how density estimate works. That is the reason why we need to use a discrete derivative for all this particular thing. Now, we can consider fx can be written obviously as this particular thing. Fx can be written as this particular thing, and this h is called the bandwidth. As I said, this is called the bandwidth. This controls the interval we are using. If we break down the estimator, this can be actually further written as, see, this can be actually further written as 1 by 2 nh, the summation of this part, x plus h is less than x I, less than equals to x plus h. Okay, and then the spread is divided into 2h to spread these points over an interval. And then what we do is we average over the sample, average divide by n to average over the sample. Now, rewriting this part as a kernel estimator is, how we can rewrite this part as a kernel estimator is equals to 1 by nh summation k xi minus x by h. So this part is actually called the kernel part, k u. Okay, where this is called the kernel function, and it controls how much weight we give to each point xi based on the distance from x. Okay, so for example, say a uniform kernel, which is actually a type of kernel. This assumes this particular function, that 1 by 2 function form, that is half when this particular value is less than 1, and 0 when this is greater than 0. So in this case, the kernel actually counts only the points within a particular distance from x, giving them equal weight while ignoring the points which is further away. So you can see that the problem of that outlier thing, how we are, how we are sort of handling that problem of outlier thing. Now the intuition which is there behind the kernel estimate is that the closeness count. Many points close to x, if the f cap x is large, indicating that there is high density in the region. Get my point? And the fewer points in x, that indicates that if x is small, suggesting a low density. Again, a smoothing parameter, as I said, that this h is the smoothing parameter. So smoothing parameter means that the small h means less smoothing. So fx will be sort of bumpy, which will be very sensitive, which will be bumpy. Some jagged feeling will be there. And a large h is actually, it gives a very smooth curve. It gives a very smooth curve. It is not sort of like this. It's a very smooth curve, very large f. However, this actually, when we are considering some large h, so there might be a problem that we are overfitting the model. So there are some rule of thumbs which I'll be discussing about. The Silverman's rule of thumb is there, and all these things are there. And when we are talking about this this kernel. So this is the uniform kernel. Also, we have something called the Gaussian kernel. Also, we have something called the Ipanechnikov kernel. So these are all the different types of kernel which are actually used, and this is the method of kernel function which is actually used to estimate fx. So this is a general approach, and this is the approach that I am talking about. That this is a kernel density estimation. It is using this approach by using the discrete density estimator on the empirical distribution function you will be getting, and you will be writing this as this way. You will be using some particular kernel. For example, just for representative purpose, I've taken that is for the uniform kernel. Lots of other kernels are there as and when what type of data is there. So suppose the Gaussian kernel is there or the Ipachnikov kernel is there. So then as and when the situation comes, will be modifying this particular kernel, and then we'll be getting this effects as approximation of this particular function. Okay. Acha, there might be one question, as you might be asking me that, Orkojit, why you are using this 2nh? What is the importance of this 2 here? You might say directly, nh. Why not divide with nh and why divide with 2nh? So if you are only dividing by nh, it would simply mean that you are spreading the probability of an initial width of h rather than 2h. However, the factor 2 is that we are correctly normalizing the density estimate according to the actual interval length, which is making the estimate more accurate. Also, the 2nh estimator the 2nh factor allows the estimator to reflect the correct density by accounting for the interval's full width 2h, that is h part here, h part this side. So the full thing we are taking. Okay. So that is because see, the width of the interval will be actually x minus h, x plus h. So how much is the total width? 2h. So if we are only considering h, because an is actually we are just averaging over the n point, so there is a size of sample. But if we are just taking nh, so that means that we are just taking one half of the sample. But when we are taking the whole 2h, so that means that we are taking the x minus h, x plus 2h, the whole width of the sample into consideration. Okay, so that is actually good. That is a good approach. Okay. Next, when we come to kernel function, there are some things which I want to talk about here. What is a kernel function? So I was telling you, I think you remember that we were talking about something called the KU there. We'll be discussing about this KU component here. And what is this kernel function? A kernel function basically is used to assign weights to data points based on the distance from the target point of x. Okay. So what it does is, for example, in the density estimation context, it is used to determine the influence of data points around x in estimating the density at x. And it has a few important properties, that it must be integrating over the entire domain of minus infinity to infinity. If you integrate the ku with respect to u, it will be coming to 1. The non-negative kernel will always satisfy ku greater than 0, so actually they can serve as probability density function. And the symmetric kernel actually specifies that ku equals to k of minus u, which actually means that the function is same on either side of 0. Sorry. uh, so yes, so the diagram will be like this, symmetric on both sides of 0. Okay. Okay, now uh, when we are talking about the moments, so the any jth order moment which can be actually calculated as this mu jk. So this is not new, something is not new. So this can be expressed as mu j of k equals to this minus infinity to infinity, as we do in probability theory. That only is done. Odd order moments will again come out to be 0, because the symmetry means that the function balances out on both sides. And the second order or the fourth order kernel, how it comes, the order of the kernel actually, which is denoted by m. Okay. So the mth order of the kernel is defined by the smallest non-zero moment. The smallest non-zero moment. So if this is existing, If this is existing, if we are saying that we are using a second order kernel, that means the first order kernel is zero. Okay, the first order kernel is zero. Again, if we are saying that we are using the fourth order kernel, then it means that the first, second, third all are zero, and that is the reason why we are using the mu4. So the smallest possible order of a kernel, which is which is giving a non-zero moment, that is called the order of the kernel. Now, there are some popular, kernel functions. So as I actually showed you that, okay, I'll just write that there is something called a uniform kernel, which is actually over the width of -1 to 1, and the structure of KU simply here is 1 by 2 when actually mod u is less than 1. There is something called the Ibaneshnikov kernel. There is something called Ibaneshnikov kernel, which actually is assuming the functional form of this is the functional form which actually occurs 1 by this is actually less than 1, or maybe even the Gaussian kernel, which actually is showing this type of structure e to the power minus u square by 2. So these are the kernels, and see that each of these kernels have something called an Rx. I'll show you in the next slides when this Rx comes. So this Rx is actually the measure of how smooth or how rough or how wiggly the kernel is. Okay, so lower roughness, the lower the value of this Rx, lower the value of this Rx function. So more smooth, more like less rough and more smooth the kernel is. Okay, so more smooth this part, the smoother the density estimate we get. And there is something called the scaling and bandwidth factor also. So suppose say that the scale of the kernel is say not fixed. So the scale can be rescaled as, so we can be doing something called the k star, which can actually be done as 1 by bandwidth a of u by b, where b is nothing but greater than 0. So this actually means that the same kernel shape can be either stretched or they can be shrunk. Okay. The bandwidth is actually what I told, that bandwidth is actually considering the jaggedness or the smoothness or the controlling the smoothness of spread. How smooth the spread will be. And this purpose of the kernel function. So you might be thinking that what is the purpose of the kernel function? So as I said that the kernel function is used for smoothing, and the kernel function actually serves as a weighting function to determine how much influence each data point has on the on the density estimate. It is necessarily not so do not think it as it is necessarily not the true probability density function. Rather, it is actually a component which is being used to build the overall density function. And the PDF, the actual PDF, that describes the actual probability distribution function of a continuous random variable. It sorts of gives the relative likelihood between of the random variable taking a specific value or falling within a particular range. And this entire PDF integrates to one over the given range, representing total probability. This is not something similar to probability density function. It is actually enabling us to estimate the probability density function. Okay. Okay. Now we have something called the density estimator that I was talking about. So I think you remember here that this is the density estimator component. This is the density estimator. We'll be studying about this only. Okay. Yes, we'll be studying about this part here. As you can see, that this is actually the kernel density estimator. As I said, that the if cap x will be approximated or estimated by this particular structure, where n is the number of data points, h is the bandwidth. Remember, there were two here, but this two went away because initially there was a mod here. So once we opened up this thing, this two just actually went there, and k is the kernel function, the individual data points. Okay, ku will always be greater than 0, and This part will always be integrated. This ku will always be integrated to 1, and then only the effects will also be non-negative. That means it will be producing a valid density estimate. However, suppose say if we are using some higher order density kernel, okay, so suppose say we are using something called k of 2 or k of order 4. These might be useful for reducing the bias. These may be useful for reducing the bias, but ku may have negative values at that time. So the value of this f cap x, which we are discussing here, that might become so that might become less than zero. So that could dip below zero, which can actually make it invalid as the density. So what my point is that do not over smooth it. Keep it till the point your moments are coming zero and you use the lowest non-zero component. But for the greed of getting a very good estimate, do not overestimate, do not overuse the order of the kernel, because once you overuse the order of the kernel, factors might come that you might be thinking that I will be reducing the bias, I'll be making it a sort of a smooth fit or a good fit, but you might actually end up getting something which is less than zero. So at that time you might not be able to tell that this is a density function. Okay, but then again, what you need to do is that you again need to rescale it. You again need to rescale it, and then you suppose say you again need to make something called if component. So if dash x, and then this rescaled estimation will actually retain the same properties as this one, but will be treated as a valid density function. Then this has to be rescaled from here to here to make it positive, because this thing you cannot be giving that because a non-negative, sorry, a negative function can't be a density estimator, right? Next is next is when we are integrating the kernel density, that should integrate to 1. Okay, so what we'll be doing here is we'll be so I've shown the calculation here, so we'll be using this part, and then we'll be replacing it with 0. We'll be making the negative differential changes, and then just we'll be substituting it, and putting that as this whole thing, and then sum the contributions over all the data points. We'll be summing the contributions of the influences rather from all the data points, and that must come to be 1 in order to be meeting the requirement of valid density function. Clearly it is written that this must be coming to 1, and this must be greater than equals to 0. These are actually the estimation to integration to 1. So this is a very important property of the density estimation, because if this thing doesn't hold, then there's no point in proposing this as a a density estimator. But then the something called the mean comes up. So basically nothing is actually, it is the mean is actually the average location of all the data points which are existing. So we compute it as like we did in our probability theory also. So I think minus is there, but it is looking very light. So minus infinity to infinity x f cap x. Okay, and then we are again substituting this part and we are doing this part. So actually nothing. Actually similarly, so this is actually exactly the average of our sample data, so that the mean of this part matches the sample mean. Okay, and as and when we are talking about the variance component, the variance component also basically the same. The variance component of the density is actually the spread of the estimated density around the mean, and the calculation actually shows that the second moment includes the two terms, which is the sample variance and the additional term, which is actually called the which depends on the bandwidth, and this term is actually called the bias. This term is actually called the bias. This extra term, this part, comes out from the smoothing effect of the kernel, which slightly inflates the variance by spreading the density around this point. So the information depends on the kernel, that which type of kernel are using. Let's see, clearly it is, and this is a function of k. Okay, and the extra term, this is actually what I said, that the smoothing effect of the kernel. And as this age increases, as this age decreases, the term gets smaller and the variance estimates gets closer to the actual. So this part needs to be minimized. This part needs to be minimized. Okay. Okay. Now what we are talking about is we are talking about bias. I'll take a bit of time here because this is very important in understanding the bias and the variance. But that's it. After that, everything is just the asymptotic components, the MSC and the asymptotic components. So that won't take much time. Here we just need to understand how calculation of bias is happening. See, this is standard formula of bias. Get my point? This is standard formula of bias. No need of any prerequisite explanation for this. Once you are considering this part equals to 1 by nh summation k, then you're talking about this xi minus x by h. So when you are taking this kernel density estimator, so and when you're trying to calculate the bias, what we try to do, we try to write this expectation. We try to write the expectation as a convoluted, in the form of a convolution, as an integral. We try to write it in the form of a convolution point. We consider the expected value of the kernel around each of this point. Okay, and the integral actually represents a convolution between the kernel k and the density function f by making the change of variables, and then we actually write this part as u for computational easiness. Okay, and then what we say is that we say that minus infinity to infinity when we are doing ku f of x plus hu du. This equation shows that the expected value of f cap x is an average of the density function f around the point x. Okay, and what we will say that we will now be using the Taylor's theory, the Taylor series for expanding this particular component. How do we expand it using the Taylor series? This is the expansion, explicit explanation before. So these are actually, this what you are seeing, that the f1, then the f2x, all these things. So these are actually the higher order derivatives, and this the h square u square h cube u cube, these things. So these are the scale. These are the terms that scale with powers of h. These are actually the bandwidths. Okay, these terms, what do they do? Hu whole square, hu whole cube. So this value increases. The whole value increases when the value of h increases. Hu whole cube increases when h actually increases. So this value actually increases when the bandwidth increases with the value of h. Okay. And now when we are trying to consider the expectation of this part, so see, nothing we are doing. We are doing exactly the same only. So we are just replacing this equation here, and this expansion we are using this Taylor's theorem, what we have done from here, and we are just putting it. What we will do is we will be opening the bracket and we will be integrating each term separately. What we get is the zeroth order term, that is this part, minus infinity to infinity ku du equals to 1. So then we will be getting the fx from this particular part. The first order term will be u ku du. Is the first order term. So for symmetric kernels like Gaussian, this integral will obviously be 0, because that actually means that this term would not be contributing to the bias for symmetric integral. And then the second order term will be again coming as u square ku du, and the integral contributes a term involving h square, specifically something called 1 by 2 this h square theta 2k, where theta 2 is nothing other than the integration of minus infinity to infinity u square ku du. Get my point? And finally, after integrating, we find that e of x will wholly come up to fx plus half, sorry, half f2x x square theta 2k, and dot dot dot. And then finally, once we have got this component, what we'll be doing is we'll be Subtracting this part, we'll be subtracting the effects from this particular component that we have just made just now, this part, and then we are left with this part. So this is actually the bias. This is actually the bias. Okay. So bias, actually you can see here that bias will be proportional to h square. So it means that as h gets larger, the bias is proportional to h square, so bias also large. Okay. Now, higher order kernels, I was talking about some bias reduction factor also. Higher order kernels are specifically designed to reduce the bias. So for example, if we are, suppose say, if we are using the fourth order kernel, okay, so then the bias term will be, I'll just use the eraser to erase this component, then it will be easier. See, why I was saying that higher order kernels might contribute to lower bias. So bias in that factor will be 1 by 4 factorial, and then this. Now what happens is the bias now scales h4 instead of h square, but it decays faster as h is like tending to zero. This part decays faster, resulting in smaller bias. But yeah. Okay, sure. So next we have the estimation variance. So I'll not go into much details about the calculation aspects here. However, the key aspects I'll just tell about the variance is that the large sample size n reduces variance and the larger bandwidth h increases with it. Also, I was talking something about this RK. So this is actually the roughness factor. So the less the roughness, more is the smoothness, and the higher order terms are the minor order terms. So actually, this O1 by n, this order actually as h is going to zero and as n increases, so this variance also decreases. I'll not go with all the asymptotic mean integrated square components and all these things. You can just take the formulas from here. This will be useful. And then we have something called the asymptotically optimal bandwidth. This is also actually, and the formula is here. So you can take the formula from here. And asymptotically optimal kernel. So criteria for asymptotically optimal kernel is when we are trying to minimize the AMSC, the kernel choice affix actually. So this is a constant depending on the kernel's order and shape, and this represents the kernel's roughness as I've already said. So this kernel stands out because it minimizes this term, making it a most efficient choice. And there are some conditions and calculations which are actually there for the kernel to be optimal. That increases to one, and the moments are there up to certain order, match specific value. And finally, we have something called the relative efficiency, which actually compares the whatever the efficiency is there with respect to the Ipashnikov kernels. So this is the formula of Ipashnikov kernel, where m is the order actually. Okay, the m is the order, and finally, we have something called the rule of thumb, which helps us to determine that what will be a very good bandwidth. For that we use what is called Silverman's approximation, and this is the main formula. I'll just write the main formula for you for the Gaussian kernel. This is actually the general formula for choosing H, and for the Gaussian I'll just write and then I'll end my talk. Nothing is there more. So H, sorry. This is for the Gaussian component, and I'm not going for the Ipashnikov kernel and the bi-weight kernel, so that requires more time. But yes, so you can use this formula for choosing that what age will be optimal for you, and like what bandwidth will be optimal for you for estimating the PDF. And then like this is how we have come to the end of the talk. I think it was pretty long. I tried to make it as much informative as I can, but in that aspect, I think it was a bit long. No worries. Some references books are there. These are very good books which can be referred for non-parametric statistics. Calcutta University also refers them for like teaching them in uh, this for their MSc course. So Fraser, Gibbons, and all these things are these two books specifically are very good books. So you can refer all these things. And so lastly, I would like to thank all the listeners who are there, and of course Moitreo for arranging this talk and hosting me for today's session. I tried to make this as much informative as I could. So thank you. This is the end. This marks the end of my talk. Thank you. Yes. 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 Is it? Oh, no, no. Wait, I'll just share my screen. I'll just share my screen. Let's just. No, you can get PDF copies. Like Deshpande's PDF, I have readily with me right now. I can send you. Yeah. Yeah. Okay. So, any more questions? Do we have? I think no. Okay. 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 Thank you, Medaloki. Also, I saw Medaloki has attended. So, thank you, Medaloki, for being in this talk. Thank you. I will take everybody's leave then. Okay. Yes. Yes.